hard to pass because the homework was worth so much.
Okay.
And,
They let us correct that one.
and also,
Are people in it right now? Yeah.
And also, like, the homeworks are like,
Homework sucks.
Yeah.
you just keep trying until you get 100%.
Because you keep submitting it. Yeah.
So you either get a 0 or 100 on every
Worst
one.
part is honored lectures. Well, I found half the time the new system, like, Fuzzy Grutter doesn't recognize the right answer.
Oh, yeah.
I've been running into that.
Okay, so then this is an elastic. We assume I touched a nerve with that class, but yes. Anyways, we're getting the dean is also retiring.
I hope you're ready for like
So
an hour, right?
there's excellent. Yeah, Gunnick is retiring too.
I've never.
Yeah, you never interacted with him. He was the department here, but department head once before.
I didn't realize we had it even until last semester.
You know what they? Yeah. Okay. I'm ready. I'm throwing things off here. I should have done it. Okay, so back there, that's an elastic substitution. If you want to jump, I jumped ahead a little bit. Like the EIU prime is equal to the moment, assumes that things are elastic, but they don't have to remain elastic. If I was just to solve this and I wanted U as a function of X, you could just integrate this, okay? So then if you want to, you just integrate this twice. U of X is equal to integral phi of X dx dx. Okay, I just wanted to show, like, if you had a nonlinear response, at this point, you could predict the displacements based off of this, okay? Because what you would do is you know what the m of x is, right? That's a given. You know what m of x is, right? Just based off of equilibrium. And I could go, all right, well, given an m of x, I come up here and I say, all right, what's my moment? It has a curvature of this. And then I would put it in here and I'd calculate the curvature. And then I'd say, all right, at another place I have a moment of this. I'd put in that curvature and I would integrate it over time and I would keep doing that. So this one right here, just integrating, works for nonlinear stuff. This is just in case you ever find yourself wanting to do stuff that you can, if you integrate the curvature and if you know this relationship. I say this because I had to do this once, but I'm way smarter than you guys. So this is by the way, this is what James noted, right, during his thing. He's like, oh, I get all these people from UW, and they're really good at, like, the technical stuff and making spreadsheets and doing these big analyses and doing, like, the stuff, but then they also don't know how to design. That's me. I went to UW. I learned stuff like this. I learned how to take a moment curvature relationship and integrate it twice to get my displacements, and it works for nonlinear behavior. Should I have to pass that knowledge to you a little bit, just in case this stuff you find interest in this more than designing. Come into my world. Come into academia. That's where you belong. Over here. If you like doing integrals, if you like doing integrals, if you like solving matrices, if you like using MATLAB, come on over. Huh? You don't have to ever work with architects. You got to work with.
Do all that other stuff.
Yeah, it works with other. And then anyway, so that works. So then just to finish it off on this elastic, and then we'll move on to show you what you really will do. I always find this interesting because there's like method behind all of this. If it's in elastic, then like I said right here, U prime is equal to the curvature, which is equal to M over EI. Okay, so then like I said, EI U prime is equal to M as a function of X. And then what you do is if I take the derivative, dm dx, that's equal to v of x. Right? That comes from equilibrium. If you look at your mechanics materials books, you would see that the derivative of the moment gives you the shear. The slope of the moment is your shear. And so that's just so I'm going to take this since this is my moment. If I take the first derivative of the moment, that'll be EIU prime. That's equal to v of x. Right? And if I take the derivative of v of x, dv dx is equal to w of x, negative w of x. Okay? And so if I take the derivative of this one, EI u prime is equal to Negative w of x. Right, and that should be familiar, especially those of you that are in, and this is probably review, you guys just covered this stuff, right? And right. But it's kind of cool that it incorporates all of that. I mean, this, right? That's what this EI is the slope. I mean, it ties back just to this relationship, right? The EI is just the relationship between curvature and moment. And then you integrate it over across the length of this thing. And then the support conditions, the different types of support conditions get incorporated with the boundary conditions that you use to solve this fourth order differential equation, right? And so it's a compilation of all of those things. It's magical. I think it's a magical equation. I really like this. And then you could take this and start manipulating even more and talk about like what the end conditions are if you have a point load at the end condition or if you have a rotation on the end, and then you can kind of work its way out and then solve this big matrix thing, which is the foundation of finite element analysis. It's all based off of this equation right here and applying different boundary conditions. You want to go into academia, Neil?
No.
Come on in, man. Come on in. Okay, so that's what's that?
Kyle will be there soon.
Hey, come on, Kyle. Come on in.
And what, 10 years in the real world? What'd Tim do?
That's what Tim did. Otherwise, you end up like me, talking to students about shit they'll never do.
So you need someone to teach practice, right?
Yeah. Things you'll never do. Okay.
Give me a department head.
Yeah, there you go. You could sign up for the department head. Someday I'll do department head. I just don't want to do it right now. I don't.
You want to keep teaching?
I want to keep teaching. I enjoy the interaction with the students. I don't know, you guys may not enjoy it, but I enjoy interacting with you and getting to know you and all that stuff. And then just don't teach anymore. You just you teach business fundamentals and you'd hate me, right?
Or you would be the one professor that could make business fundamentals interesting and enjoyable.
I'd be like, why would you ever do this?
You'd be like, so you guys don't have to know how to do this at all. This is where
Yeah. One thing I've always had a problem with senior design is that you guys really focus on stuff that you're not going to do until like 20 years down the road, like the project management and stuff like that. You're not gonna do any of that. When you first start as an engineer, you're crunching numbers, checking shop drawings, doing like stuff. You're not writing proposals and presentations and stuff like that. I've always pushed for like they should do like the steel, like Utah State University, their senior design is the steel bridge competition or the concrete canoe competition, and everybody does one of those, and then the winner of the local one then that goes on and does and that's what their senior design is. I think.
You should push that. Pass SD to win.
Sure, yeah, pass. That's what we're doing in here. Remember, that's what we're doing in here. You gotta. Whichever team wins gets an A, and the one that loses gets an F.
Yeah, I'm entering the transfer portal.
Yeah. Oh man, it won't. God damn it! This update is the freaking worst. Okay, you'll do this for various boundary conditions. So this is one thing you could do, right? Obviously, you could do this. This is how I would do it if I was in the real world. Then I'd get fired for wasting too much time, right? That's one way to do it. The other way to do it, I think, probably how most people would do it now, is just tables, right? Right, in AISC is the easiest one. They're the most complete, right? You know what I'm talking about? You look up, it's the back of the beam tab. I think everybody should have a steel manual, right? Was it table?
322.
That's right. 3-23.
That's proof God exists.
Table 323. Is that what you guys say? Did Tim say that? Are you guys saying that? That's good, Connor. I like that, dude. That means you don't need to know the fourth order differential equation. You just
That's
that's the same. God has provided table 3-23.
so much trouble with Kirsten last fall because
Because you kept saying that?
no, because we were doing shear moment diagrams and it's like I'd immediately default to.
Oh.
Too, if I do not like finding out that table exists.
The table exists,
as
sure.
they're figuring it out by hand.
Also this, right? Finite element analysis. It turns out if you do finite element, that's all built into that, and you don't even need to know those tables. Just put it in a computer program, right? Or there's there's different like EnterCalc. Everybody use EnterCalc in the yeah, right. The EnterCalc and stuff. That's like element by element design is what those are, right? Yeah. And so you just got to put in the loads on the outside, and it'll tell you the deflections and everything else. So, but again, it is important to know how to do it by hand. Then you really appreciate the other. You worship the other methods that exist. Okay, so that one's easy. Okay, what you do with external loads is the same thing you do with all other external loads, right? You got to be, the things that get a little bit complicated would be like, what you use for E, right? What you use for E, what you use for your I, things like that. But it's just gross section properties. You have to come up with the EC for your concrete, so you're going to have to calculate what that is, which Anika, is it Anika? 57,000 square F5C, right? That's what you do for your E and looking that thing up. But other than that, it's the same way, okay? But where things get difficult is deflections from pre-stressing, okay? What do we do with these, right? Well, it turns out there's a free program. I looked at downloading that, and I don't have a Windows computer. It's all, remember how, fucking James, I forgot him already too. James was saying, there's a free program that you could use to WashDOT that does the analysis. I don't know, for the big beam competition. You might look and see, or compare it or something like that. I don't know. I couldn't get it to work because I'm not stupid with a PC.
Even like run through a virtual desktop.
I could, but then they wouldn't let me install it because I didn't have like administrative rights to
If you were the department
talk to Ernie. If I were the department head, I think we might have an internal candidate. I think it might be Katie. Yeah. Yeah. She wants to do it. Yeah.
She could make business fun.
She could probably make business fun. Did you guys take a class from Katie? What was the class? Oh, okay. Yeah. I think
Wait, was she?
fluid mechanics for her? Yeah. How'd it go?
No.
It was super easy.
Was it really?
You had
had it with Joel.
for fluid mechanics?
Oh yeah, with Cahoon. Oh man, you lost, Thomas. You lost, dude.
No, he lost.
Oh no, sorry, you won. Yeah, you won. You lost.
Everybody else.
Sorry, that's what I meant.
In fact, he won football. So respect.
Oh, you guys went to it after my class, right? Did you have fluids with Joel right after my class? It's after structures 1, you would go over there. It's 3:00 in the afternoon on it.
And his last class.
His last semester.
He's like, "Fuck you guys."
Yeah.
He didn't?
No.
Because he stopped working by then. Is that what it was?
Because it snowed too much.
Oh,
I didn't
yeah.
want to drive.
Oh.
No,
Okay.
because Ravi was also in Japan for our final in geotech, so
Which helped us.
that's true. I heard.
Okay, bring it around. I'm the one that starts these things, and then I can't bring it back under control. Okay, so one way is going to do this equivalent force method. We're going to turn internal loads into equivalent external forces, I guess, right? That give same conditions. Then use method above to get displacements. Okay. Once we know the equivalent loads, once we know the equivalent loads, then it just defaults to using one of the methods up above. Okay, and so we got an example of that. Okay, so we have this. Right, and you can see our CGC goes right across here. I want to make that a different color. This is an example here, right? I got my CGC going across right through the middle. My CGC. Okay, and that's my pre-stressing that's doing that. It's a draped pre-stressing section that goes across there, right? So this right here, This is my EP. You son of a gun. Why? You son of a gun. I fucking hate this thing. I'm gonna throw it out the window. I tried to draw an off diagonal oval this morning and then it just... I got freehand my lines here. That's EP, right? And then down here would be EP max. Okay. And so the moment that this would cause, right? This would cause a negative moment, right? Because it's causing it to pop up. And this big pre-stress is going to cause it to pop up. And the moment would look just like that. Right? It would be a negative moment. Like that. That's what my moment diagram would look like from the internal forces, right? And this maximum moment would be FP EP. EP max. And that's the maximum moment. And so what we do, right? So that internal pre-stressing forces or internal pre-stressing layout like that would cause an internal moment that looks like this. So what you do is you say, all right, what kind of point load, right? Or what? I guess I just gave it away. What kind of load would give me a moment diagram that would look like this? A point load. That's right. That's fucking right, dude. That's right, Gavin. Good job. You listening. A point load, right? A point load where? In the middle. Which direction?
Up.
Yeah, yeah, you're wrong, son of a bitch. Oh man, you thought you had it, dumbass. Honestly, the way you guys draw shear moment diagrams is 50-50. About half of you would have said that too, I think, right? You guys' shear moment diagram. Oh. You guys are a little bit better, but like.
Now I'm teaching people how to do
They're teaching them how to do it. Their minds are blown. Yep. Yep. So this would be equivalent, right? And that's the idea, right? What is the equivalent force that would give you the same moments? Right? That force diagram would give you the exact same moments. Let's do this. Boo. Oh. Boo. Boo. Oh. Boo. Oh, now it's letting me rotate it. All right. Does that show up? See, now it's letting me rotate. But then watch this. If I make a circle, obviously an oval. That's an oval. But if I wanted to rotate this thing, see, it doesn't let me do it on this one. See? It's not a circle. It's an oval. You motherfucker. See, it's an oval, you sons of bitches.
Grab it with your
You're right. I don't need to rotate a circle. I know that, motherfuckers. I know that. I said.
Like, you can grab it, tap it, it should come up with like a cut option, and then you just paste it back in, and then you can rotate it.
That's so much work.
Yeah, but that's about the only
Yeah, cut it. Cut it. Paste it. Oh. Oh, Sean.
Works for me.
You have an old one.
You have a real computer.
No, you don't. Oh, you have a computer. You're an iPad?
No, it's Samsung.
Oh.
Real
One of those guys. Anyway, so over here. So that give me the same one. Over here, though, what's the moment? Oh, there you go, Gavin. What's the moment at the center of a simply supported beam with a point load?
PL/4.
Yes. Negative QL. Oh, you did it there, yeah. Negative QL/4 in this case, right? Because that's gonna, and this I guess would be negative
Why do you
FP.
use Q instead of P?
Well, I don't know. I just did it because I wanted to. I think Stanton does it in his notes. He talks about it. I think it's an equivalent. Q for equivalent. Equivalent load.
There's probably a P somewhere else. Yeah.
Equivalent load. Okay. And so what we do, right? So you got to do this. So you say QL/4 is equal to FP EP max. Right? So you set those equal, they're equivalent to each other, and we could solve for the Q that you would need. So in this case, the equivalent load you'll put on there would be Q is equal to FP EP max times 4 all over L. Okay, so that's the load that you would put. That's the equivalent load that would give you the same moment and same type of behavior. What is the displacement, Gavin? What's the displacement at the center of a beam, simply supported beam with a point load?
I got it.
What do you got?
PL cubed over 4080.
Hells yeah! Welcome to the hood. Oh, you did? But then why didn't you know that then?
Well, I knew it was like 48 DI.
Okay. Yeah, you're still. I'll let you in the hood for this one. That's okay.
Can I be in the hood?
No. PL over 4. That's a neat. Why did I make that?
Do you want to be in the hood?
QL cubed over 4080i. Yeah, you do. We're cool. They're cool, right? And so then if you substitute this in now, right, you take 48, you know. And so you take this. Uh-oh. You take that, substitute it in there, right? And then you get the displacement. Just to show you, the displacement you get from that eccentricity there would be negative FP EP max times L squared all over 12 EI.
Where should negative come from?
Well, it's there. Well, because we want a downward deflection. So I guess maybe it'd be positive. I guess it's like, I dropped the negative because they were both negative, and then I dropped it. I guess this would be a negative. I mean, just to say that it's going down. Sometimes we say the positive is going down, so. Because, but it's going up, though. It's going up. It's going to deflect up. So it would be negative. I don't know what this. The hood knows that that's going to cause it to pop up. I guess this would probably have to have a negative. There. Oh, actually, what it is, this
FPEP should be negative.
are these both. See, these are both. Oh, FPEP.
It's going to give you
Your
piece
QL over
positive
4.
in this case.
Your QL over 4 is going to be negative.
Yeah,
Yeah.
you wrote it in the moment diagram.
There we go. There we go. There we go. Okay. So that's it, right? So that would be the displacement, right? So if I put in the pre-stressing that looks like that, that's what the displacement would look like, okay? If I had a constant across the whole thing, right? If I did not have it go up and down, if I had a constant go across, what would my moment diagram look like then? Straight line. My moment diagram would go like this. And then what kind of load would give you a constant moment across the whole length? Oh. Yeah, concentrated moments. Maybe academia. Huh? Yeah. Concentrated moments on either end, right? In this case, it would be the down, it would be like the get it to pop up. And so then there'd be an equation in AISC that would be the displacement of something with concentrated moments. And so that way, and then you would have to make that concentrated moment would just be FP EP is what it would be. Okay? So then, or Stanton put this together. I've never seen this anywhere else, but I like this one. Or Stanton notes. Or Stanton method, which I like this. Okay, and what he says is you use this thing over here. Use this, and we'll do it. We'll use the one up above as an example. Okay, so if you have a strand pattern that looked like this, I don't know why you would ever have a strand pattern that looks like this. If you had a strand pattern that was constant like that one, or you have a strand pattern that it's down like this, or if you have like they do a lot of double harped in some applications where they hold it down in two different locations, or if you have a draped section. And so what it does is it says if I have one that looks like this, I'm going to calculate delta 2. And it's going to be half of what I get for delta 2. And then here is delta 2 down here, okay? Or if I have one that looks like this, it'll just be 1 times delta 2. And so I put in, that must be for the two concentrated moments down there. Or if I have this, it'll be 2/3 delta 1, where delta 1 is calculated from this, okay? And then use these other ones. So in our situation from up above, we have this case, right? Where delta is equal to 2/3 delta 1. delta is equal to 2/3 delta 1, right? Delta 1 is equal to EP FP L squared all over 8 EI. Right, the P's that they have down there is the same as what we're calling FP, right? So that's delta 1, and then I do 2/3 of that. Delta is equal to 2/3 of FP EP L squared over 8 EI, right? And then that ends up being what we had up above. FP EP L squared all over 12 EI. Same answer. Samesies.
So that'd be negative as well.
Yep, I wasn't done, Neil. I was going to say, what's wrong with it?
It's just where he doesn't have a name.
I know. I guess you got to be part of the hood. You got to know which direction it's going.
He's wrong.
He's wrong. Right. There she is. Right. So you get the same answer. So either one. I thought that's kind of neat that this little approach down below works pretty well for it. And I think you could do a combination. If for some reason you had not this case where this one goes where it goes right to the CGC. If for some reason this was offset. I remember I have to do this. I don't think I make you do it. But if this is offset where it went like that, right? That didn't go up to the CGC, that case would be a combination. It would be a combination of this one and this one, right? And then you'd work the two together. And then you could still get the deflections based off of that, right? And so if you were to do this, by the way, if you were to do this like with finite element analysis, and you were like, okay, I'm going to model this thing using finite element analysis, which post-tension floor design has that built into it. You could do that. What would have to happen if you were just plugging things in, it doesn't have a way, like if you're using VA to do this, it doesn't have a way of putting tendons in it, right? But what you would do is you would put in, the regular loads on your structure, and then you would go through and you would put a point load on it in the middle, just like this, that would have the magnitude of this. You would put that equivalent force. Oh, because we call it that positive load. You put it in so it's going up, whatever. You would put it in an equivalent load in there for that, and then you would get the displacements based off finite element analysis. But you would put in that equivalent load to do that. You wouldn't have to do this stuff because VA would take care of that for you after you put it in there. Okay. What are we doing? All right. Cool. I think the next homework you will calculate immediate deflections. Okay. This is another one just in case. We're not going to do this as the homework or anything, but immediate deflections in cracked beams. What do we do if you have cracked beams? And I briefly blew by this last time, but let's talk about that. Right? Typically, this isn't an issue. Right? Usually design, pre-stressing, not to crack. Right? That's the point of it, right? Is we're spending a little extra time and money to make it so that it doesn't crack. But if for some reason it does crack, I don't know why my text is so small and I can't change it. They couldn't change it earlier. Okay. Typically not an issue. We designed it to not crack. But if it happens, right, this has to do with the classification, right? If we consider this thing as a U versus a T versus a C section, right? If it does crack, it is a nonlinear problem. Right? We can do nonlinear FEA. Right, where you would integrate curvature along length, but we're not going to do that. There's also approximate methods. I'm not good at this. Oh, you son of a bitch. Oh my God. We have ACI. There's ICR. And bilinear. Did you guys do bilinear method? Or you just did I effective? You probably just did I effective. Okay, you could do ICR and bilinear method or I effective. CPCI chapter 5 for an example. If you want to see that at play, we're not going to do it, but if you want to do it, you can do this. These methods are empirically based. Right, just based off of a bunch of test results. Weird, because they assume cracked over whole length. Right. And this is what they look like here. You come back to that moment curvature relationship we just talked about. Moment and curvature. And one method, you go like this. This is the bilinear method. They assume it's EI up to a certain point. They assume that this is EI. And then the slope after cracking, this one, and that one is EI crack. And so you end up doing two deflection calculations. You do one up until it cracks, and then you do another deflection calculation afterwards. You use those equations up above, and you do the leftover load that's there it's softer, and then you have this more deflection. Or the I effective just cuts the corner. Goes like that. You son of a bitch. Oh, you son of a. I don't know why it does that. Why are you turning my? I'll stop showing there. This slope here would be EI effective. I think most people would do the EI effective one if it's cracked, right? But again, you're not going to end up in this realm very often. But if you do, you could do that. All right. Next time we'll talk about long-term deflection, because what's been floating around in all this, I keep saying immediate deflections, immediate deflections, immediate deflections. This stuff doesn't take into consideration pre-stress losses and creep and stuff like that. So we have to, basically what you do is you calculate the immediate deflections and then you modify them to account for the long-term effects. Right? We're going to use this one, or we're going to use a method that PCI puts together that you just have these factors that you apply. Okay, deflections down, these are at erection versus the final, and then here's the factors that you end up using. They end up being a lot, right? I mean, look at it, 3.0, right? So long-term deflections, these things continue to move over time significantly. Okay.